Okay, let's start today with a discussion on block ciphers. And one particular cipher we'll study is DES cipher if time permits. Okay, contents I have taken from all these resources, primarily from this. You go to Berkeley, University of California, Berkeley site, and go to or research CS161. You get into the website, and there is a book there. And there are PPTs also, right? A lot of information or material is there, so you can use that. And the second resource that I've used extensively for crypto part is this lovely book by Professor Parr, Christoph Parr, and Jan Pezel. And they have series of video lectures available on YouTube. I just love it. I mean, it's just a lot of things become clear once you go through this video lecture. So if you're interested in crypto, I would very strongly recommend to use this book, for your understanding. And it's very interesting topic. Okay. All right. So where are we in the course? We have completed all these topics, and then we have entered very important part of security, which is cryptography. Okay. So in cryptography, we have seen there are essentially two kinds of encryption function or crypto function. One is symmetric, other is asymmetric. We will study asymmetric later. Okay, within symmetric we have again two parts. First is called block ciphers, which most of the encryption technologies use today. Second is stream cipher. Stream cipher is used for streaming data bits, right? And we have to do it at very fast pace. Okay. We have already studied one time pad, OTP, and also study a stronger form of security requirement, which we call it indistinguishability, IND-CPA, under chosen plane attack, right? So this can also we have studied. Now these are the topics left out to study. I hope we should be able to cover most of these, but I will need at least 5 extra lectures because we are going very slow. So there are many students who are from the second year and they have not done basic courses on many things, right? Algorithm architecture, and so on. Okay. Computer network. So we'll have to repeat a lot of things. We'll have to build the concepts right from beginning. Otherwise, for example, I start talking about security using IP. Now you should know what IP is, right? Okay. So it's important that you concentrate in the class and at least give me 5 extra hours. If you want to understand, I can easily finish the course and otherwise whatever lectures available. Okay, this is very important chart. You can get it from internet. In fact, similar chart that goes up to 2022. Okay, it says that cost of attack, this is the cost of attack, as dotted line, is decreasing very fast. Okay, over time. It means that you can now, if suppose you have to spend $1 million in 1980, now you can do possibly for just $100 or even less. And then complexity of the attack is also increasing. Earlier these attacks were a simple hack, but nowadays there are something like very planned project managed attacks, right? Okay, so the complexity of attack is increasing while cost of attack is decreasing. And also we can see that internet is also growing at exponential pace. Okay, internet is the de facto standard for communication today. Okay, So it means that everything, every device, every human being is going to be connected over internet. And then this course becomes very relevant because you should be able to create awareness and help people to save yourself and others from being attacked. Okay, all right. Okay, give me a minute. Just clean up my. Okay. All right, this is where we are. Okay, I will switch off video. All right, so last lecture, what did we study? We studied about symmetric tree cryptography. Okay, I'm revising this because those of you who are not there can understand it, because today's lecture is important. Okay, so idea is that Alice should be able to communicate with Bob securely or confidentially over internet or insecure channel. Which is internet today. And there is an interesting character, Eve, eavesdropper, or we call it Eve, and she can see whatever is being sent. So what we want a mechanism where whatever Alice is sending, although may be visible to Eve, but in some forms that Eve cannot understand. So the communication remains confidential. For that, we have devised a simple method. We mean that researchers in the past, and here we have very simple encryption function, and other hand there is a decryption function. Okay, input to this is text, plain text. Output is ciphertext. This ciphertext goes over in secure channel, where the data can be seen, whatever being sent is seen. So it means the ciphertext can be seen by everyone. Okay, yet we should devise schemes such that in between Eve cannot make out what is being sent. Okay, now very simple thing that has happened in the past over many centuries prior to this scheme was that this encryption function was all the intelligence lied here. Okay, in this encryption function, right? For example, very simple encryption function which you have used in your childhood is that change A to C, B to D, E to C to E, and so on and so forth, right? Just shift characters by 2 positions, right? So this is, so if you write something using this one here, using this kind of characters or normal characters, it gets converted into corresponding mapped characters, right? So this we call a ciphertext. Now this ciphertext is very simple to break. Okay, and secondly, this algorithm that we are doing, or encryption function, which is the shift it character by 2 places. Okay, if somebody comes to know about it, then all the encryption is broken. So now how to keep this encryption function confidential has been challenged in the past. Okay, ultimately it gets leaked out. Okay, so then a researcher called okay one researcher came out with the idea, okay, that this encryption function or decryption function should be known to everyone. However, what is important is the key. Key should remain confidential. Now we are going to use here the same key for encryption and decryption. It means the key should only be known to two entities. All right. Okay. What is the law called? Where key is important, not the encryption decryption function. You studied this in last class, right? Anyone? Remember? We, we have studied a concept of principle, security principle, that security cannot be provided with obscurity. Then we said that design of lock should be known to everybody. Only thing important is the key. Okay. All right. So we discuss this point. Okay, I'm asking you guys. Okay. Can you answer this question? What was the law called? You guys, are you sleeping? Hello? Are you there? Are you guys listening or not? Wow. Can you unmute yourself and answer? I'm not sure if you're trying to answer this. Oh, there's some problem, it looks like. Okay. Somebody's answer is the Shannon's maxim, right? That's right. Okay. Oops, let me try to unmute you guys. Can you just unmute yourself, or there's some issue? Just a minute. Yeah, it says that unmute all. Let me see if I have unmuted all. Okay, you can unmute yourself. It's a message says, right? So all right, let's move ahead. Okay, can you hear me?
Yes, sir.
Okay, all right, thank you. All right, so this is what we have studied, right? Okay. Okay. All right. So only key should be known, nothing else. That's the. Just a minute. Wow, a lot of things are happening today. Give me a minute. My pencil stopped working. I don't know why. Just give me a minute. Give me a minute. Okay, back. All right. Okay, so now let's move ahead, right? So this is the concept that we studied, and the principle that we have been talking was this Kirchhoff's principle. Please go through it all over again because it's important. Okay, so this is the definition we have seen. Is a plain text that is being encrypted. Encryption algorithm corresponding to this encryption algorithm is decryption algorithm. Note that this encryption and decryption algorithms are well designed. So there is a, if you are using say DES encryption algorithm, you will have to use DES decryption algorithm. Now other important thing is that there is a one-to-one correspondence between plain text and ciphertext. Okay, so if n bit of plain text we are using, there will be n bits of ciphertext. Okay, now the key size depends on this algorithm, whether DES or AES or whatever. Larger the key size, more secure is the system, right? As we have seen earlier, this concept of key space. All right, so these points we have seen, and then we have seen these properties that are required. Then we have looked at IND-CPA security, and then we studied one-time pad. All right. Okay, let's move ahead. Okay, so this is where we are, and today we will study block ciphers. Okay, so here this is the cryptography cipher types. We have symmetric cipher, asymmetric cipher, block cipher, stream ciphers, and what we are studying is block ciphers. Okay, now look at these two diagrams, right? One is a block cipher, other is a stream cipher. A cipher we call it is nothing but encryption function or decryption function, right? Okay, now here in block cipher or block encryption, we take a block of n bits. This is a block of n bits, x0 to xn. This is a block, and then give this as an input to cipher or encryption function, and output is n bits y0 to yn. Of course, for that we use key k. Of here we assume is key is of k bits or k bit key. Okay, all right. So input is a block of n bits, output is a block of n bits, and note that there is, what we also see here is what is the relationship between first bit and second bit and third bit, and based on that output is created. Okay, we'll come to that point later. And second is stream bit, like you stream bit of data, a stream of bits of you're streaming bits, for example, on some channel. Okay, then you want to very quickly encrypt that. So what you do is that very simple stream cipher could be, you also use stream of key bits. Okay, let's assume that stream is x0, x1 up to xn, and output is y0, y1 and yn. Then we can say y0 equal to x0 with some function, maybe exclusive OR of k0, something like this. This could be some function. Okay, so this input is 1 bit, output is also 1 bit, and this transformation of 1 bit to 1 bit, there's a 1 to 0 or 0 to 1 or 1 to 1, depends on the key here. All right, so repeat, we have two types of ciphers, block ciphers. So most of the time, about 90+% time, we use block cipher. We encrypt full block. Encryption of any plain text bit in a given block depends on every other plain bit in the same block. So encryption, when we are encrypting something, for example, y0, output is a y0, this depends on all this. Okay, all right. So it's very commonly used for internet application. Now stream cipher encrypts bit individually, as we have seen here, x0 to y0. Okay, it works by adding a bit from key stream to plain ciphertext bit, right? Okay, basically you use key here and then use some function, okay, and generate output bit. All right, it's very small and fast. For example, it's embedded devices use it, like GSM phones, or maybe even modern phones use streaming cipher, because it, you don't have time here for processing of number of bits. You're creating a block and then encrypting that, because creating a block or making streams of bits into block and then transforming block will require time. However, all internet applications, like we are browsing web page and so on, we'll use block ciphers. Okay, so we are now we will focus x2 classes or 3 classes on block ciphers. All right. Now, one important thing into symmetric key cryptography that we have seen, that we have to send the key across, right? Both parties have to use the key, and number of keys can be very large. So we'll look at this problem little later. Okay. However, you have to see that, in case of OTP, one-time pad, we are using key only once. So that's the reason we are able to get IND CPS security. Okay, but here in practice we cannot use the key only once, so we'll have to use it for certain number of times. Okay, for example, email, what do? When you send email, you may have Google email or maybe Microsoft based email program. So what do? Do you use the key for each word in a message, or your email message contains some 50 lines? What do they do? In general, you need to find it out, but in general you can think that for each email one key is used. Okay, it means sender and receiver should have a key that will be exchanged, and for encrypting the email you will use one key, and same key you will use to decrypt. Okay, all right. Now the question is that when we are using the same key for multiple blocks, because your message, long message, email message, whatever, we split into number of blocks, then how can we not leak information? Because we have seen earlier, we can always leak information, right, if key is the same. All right, so we'll look at this. We'll solve this problem later, that when we split the large message into blocks, and blocks may, then if you're using same key to encrypt and decrypt blocks, multiple blocks, then we don't want information to be leaked. And that's how there's something called modes of operation that we'll use. We'll come to that part later. All right. Now here in block ciphers, okay, we use blocks of fixed size. Generally, this size of block is 64 bits or 128 bits, right? So if you a long message, split this into block, and blocks, let's assume, is for 64 bits, and then you encrypt using function, some function, encryption function, and output is again a block of say 64 bits. Okay, so we'll have to cut the plain text into chunks based on block size, encrypt each block size separately, and put them together. So initial message may contain, say, for example, 2 blocks, so block 1 and block 2. You encrypt them using the same key. Okay, and then this output, then for this input we can say that this is the output. Okay, So basically encrypted text or cipher text, we are putting them together to get the overall output. Okay, any question? Now let's look at the diagram again. So this is a very simple diagram which explains everything. This is encryption function here, decryption here. It gets plain text of n bits, it generates output, the cipher text of n bits. It uses k bit keys, right? Okay, all right. So we can mathematically we can show it this way. Please go through it. Okay, all right. Okay, so three properties that are required: correctness, efficiency, and security. Okay, correctness means that, you know, given one message M, okay, when we encrypt this and then we decrypt it later on, it goes over channel and we decrypt it, we'll get original message back. Efficiency, it means that it should be fast, and security means that it should behave like a random permutation. Okay, what do you mean by behave like a random permutation? So looking at output of encryption, Eve cannot make out anything. It should look very random. Okay, all right. So if you have done the graph theory course, you can understand this slide easily. EK, that's encryption using key K of message M, is a permutation, which is a bijective function, right? Okay. So it means that each input must correspond to one unique output. Okay. So one of these is bijective, another is not. Of course, it's written here. Okay. So this is a bijective function because this is a one-to-one mapping. Okay. This is not bijective because it's a many-to-one function. So EM or encryption function should be bijective function. Okay, all right. And if it is not bijective, then essentially if you have one output, okay, then it may correspond to multiple inputs, because multiple inputs, if it's non-bijective, will map onto the same output. Okay, so if you have one output, if you decrypt it, you will get two inputs or two plain text, which is incorrect. So it has got to be bijective because this is exactly one-to-one mapping. Okay, any question? All right, let's move it. So block ciphers should behave like randomly chosen permutations, right? And one simple test is that one of them, so we can call it distinguishing game. So we get two boxes here, which does encryption, which both do encryption, and one is randomly chosen permutation, and other is EX. So in one of the box we are doing EK, okay, encryption using K. Other is randomly chosen permutation. Okay, all right. So Eve should not be able to distinguish between the two with probability more than 1.5. Probability more than half. All right. So it should look, so basically in simple words, encryption should, when you do encryption using any key, now key is of course a random thing, the output of encryption function should look absolutely random. Okay, all right. Okay. Now what is the key size we take? We take normally 128 bit or 256 bit. Is it sufficiently long? How big is 2 raised power 128? Okay, you go to, for example, Goa and go to biggest beach there and count the number of sand particles, right? Do you think number of sand particles in Goa beach will be more than 2 raised power 128 or less? Anyone?
Less.
It will be less, right? So this is very good. This is very, very big function, right? So we can simply approximate it, and we say that 2 raised power 10 is approximately 10 raised power 3 because this is 1024. So we can say it's approximately 1000. And then 1, so it means that 2 raised power 128 becomes almost equivalent to 10 raised power 39. Okay. And then we look at one hardware, because you're decrypt using some hardware, right? Some computing you'll have to do. Okay. And then that can try 1 billion keys in 1 nanosecond. Okay, that's 10 raised power 8, 18 keys per second. This is the speed of operation of that hardware. Okay, then on that hardware, how much time you are going to take? And this is a quite fast speed, right? So now it means that now we are going to do this simple calculation, 30 trillion years using this hardware to break open the key, or using brute force attack that we have already studied, right? Okay. Already we have studied in context of password, but it's exactly same thing. Given one output, keep try all inputs until you get the specific output, right? Or given here is a one-to-one mapping, so given one decryption, given one output, you do reverse of that decryption function and then try to get something and try to match with something. And so there are multiple ways of doing brute force attack. So now this is very long time. Okay, let's look at other ways, right? Now let's increase the key size to 256. And then you say that now we can use not only one computer, but we can use as many computers as possible. Okay. Now you'll see that the volumes of that computer, number of computer, will be equivalent to 7 times 10 raised to 15 suns, while each computer takes just 1 cubic millimeter. All right. So brute force attack on modern ciphers is not possible, assuming the key is random and secret. That's an important point. Okay. Obviously, block ciphers have got to be efficient. They should work fast in nanosecond, microsecond. Otherwise, no one will use it. All right. Okay. Now there are 3 types of encryption standards that are in use. First is called DES, that we'll study today. Second is a type of DES, essentially doing 3 times DES in a sequence. So do DES encryption, then take output, then second DES, second time DES, and third time DES for the same input, and what you get is output. It's called 3 DES, right? And then something that is in use is AES standard, which you use in almost all applications like IPsec, TLS, Wi-Fi connection, Skype, whatever, right? Okay. Now, before we study block cipher primitives, because both in DES and AES, these are common encryption or common ciphers, are the 2 important ciphers. And these 2 ciphers, we use 2 functions. We use 2 important functions. These were given by Shannon, right? You would have heard about Shannon's name in if you do EC course, electronics communication courses on communication, then you will study about Shannon's theorem. The same Shannon, great scientist, has also studied cryptography and say that we need 2 functions in encryption decryption function. First function is confusion function or confusion operation, that is obscuring the relationship between key and ciphertext. Okay, so there is a key, and using this key we generate ciphertext. So we need to have this function which will not show any relationship between key and ciphertext, right? And this is done using substitution function, which we'll study later. And second is diffusion function. which is nothing but bit permutation, right? So where influence of one plain text symbol is spread over multiple plain text symbol with the goal of hiding statistical properties of the plain text. It means that we'll look at diffusion function a little later. Okay. Now we have confusion element and diffusion element. Now we cannot use, Shannon said that we cannot use confusion and diffusion only one time. So you'll have to use confusion and diffusion multiple times to create product ciphers, right? So we have input X, we diffuse it, then we use confusion function, then second diffusion function, diffusion. You do it certain number of times, then your output is reasonably secure, right? So all modern cipher have excellent diffusion property, that is changing one bit of plain text results in an average of change in half of the output bits. It means that just change one bit, as we discussed earlier, its impact is in large number of bits. For example, you take x1 here 00101011 and send it through block cipher, you get this 10111001. Note that this is just an example. Now you take the string, second string x2, where this only one bit is changed. This single bit is changed, right? Instead of 1 here we have 0, and send it through block cipher, and you see the output is 10111100. So there are many bits that have changed here. From when you compare this with y1, you'll see many bit changes, right? So this is called diffusion function. Okay, with this knowledge, let's start discussion on first cipher, which is called DES. Note that this is a symmetric block cipher. Okay, it was designed in 1970s. Now it's done by NSA and IBM together. Block size is 64 bits and the key size is 56. Now many people may ask this question, why 56? Initial design was different, but NSA influenced it to change it to 64 to 56 bits for reason they know better. Okay, they thought the 56 bits are good enough, so I have 64 bits and so on and so forth, right? So this algorithm DSA remains essentially unbroken for 40 years and is still in use. Many legacy systems still use it. However, modern computer speeds, because now we have GPU system and then multiprocessors and so on, you can have thousands of processors on a chip. Okay, now you can do a lot of computation over, at very fast speed. So now for modern computer, breaking this key size, which is 56, is not difficult. Okay. Now, one answer of this, one solution of this, use this DES 3 times, as we discussed earlier, is called 3 DES. So use this 3 times. Okay, all right. So now we can see this is a plain text, whatever is the message size. Okay, split this into blocks, take 64 bits, that we call this block. Okay, this is a plain text. Now output is of the same size, 64 bits, and key size is 56 bits. Any question? Okay. So there are 3 phases. Now this looks kind of monolithic system, right? A black box looks very simple, like this, but internally there must be some structure, some architecture. So we are going to discuss this architecture. In terms of process, it has 3 phases. First phase, second phase, and third phase. In first phase, you do initial permutation. Second phase is the heart of this, and you do 16 rounds of some function, which is combination of permutation and substitution that we have studied just some time back, confusion and diffusion function. You do 16 times. And at the end, you have third phase, again you permute, which is inverse of original permutation. Okay, all right. So the DS function will look like this, and please go through this book, and the PPT is available on the website. and also wonderful lectures by Professor Parr. Just wonderful lectures, right? Okay, so this DES function can be seen as initial permutation of these bits. So this is input or plain text. Okay, then encryption round 1. Now you'll have to use, note that for this there is a one key, and then you have to generate from this key multiple keys, sub keys, and there are 16 rounds. It means that 16 sub keys are to be generated. These are 16 sub keys, and for each round you are going to use one sub key. Is called encryption round 1, which consists of diffusion function and confusion function. Okay, and then so these are the 16 rounds, and then the final permutation is there, and then you get this output. Any question? Okay, so the same thing depicted here. The 64-bit plain text, the 64-bit key. So now the algorithm takes 64-bit key, and from that it generates 58-bit key, and then from this 58 we create a sub key of 48 bits. Okay, and these are round 1 up to round 16, and then we have last permutation function, and then we get the output. So basically we can see that we have initial output, initial permutation, then 16 rounds of confusion and diffusion, and for that we use sub keys generated from the main key, and then output of this 16 round goes to a inverse of this function. So inverse of IP function, initial permutation function, right? So this is it. All right, so now let's look at what goes on into each phase. Okay, like each phase, each round here, right? So now this is the plain text. After that we do initial permutation, and now here the game starts. This is the key K. Now key is initially that we take a 64-bit, and from that we generate 58-bit key, right? Because we say that we are using 58-bit key here. Okay, but in overall input is of 64-bit, and then we have transformation function here. Okay, and then from this we generate 48-bit key. Okay, all right, now note that this is first phase. For the second phase also we generate sub key like here using another transformation function, and then second key will be generated. Take this key, and then we'll have to apply it to the data here. So in order to do that, we split the input that's coming from top into two halves, left half and right half, and this 64-bit initially, so we have 32 bits here and 32 bits on the right half, and then take this key and then apply this to a function called f function, and output of the f function you exclusive OR with left 32 bits, and then we swap this. Okay, so right 32 bits come here, and then the output of this f function comes there. The question now I can ask you is that which of the two have been encrypted? This one, left bits are encrypted or right bits are encrypted in this phase? Anyone?
Left.
No. Oh, yeah, absolutely right. Because right bits are coming right here, which is encrypted. Next phase it will get, because left becomes right becomes left here. Now next phase this will get encrypted, right? So now we do this for 16 times. All right. And at the end of it, we will do reverse of initial permutation and get the output. Okay. So this is the way this DS operates. This is initial permutation. How initial permutation is done? That this is the input, and then this is well defined way, right? So first bit becomes okay. In the output, first bit becomes 40th bit in the output, and 58th bit becomes the first bit, and so on. So now the question, some may ask that why in this way? When they designed, why did do this mapping, right? Well, again, there are many reasons, but of course, at the end it turns out that initial and final permutations are done. Of course, it gives some, uh, it does some diffusion function, but more important than is that it was designed to help hardware. Okay, of course we will not go into too much of detail. Okay, but it's generally is done this way, right? Okay, now what is the f function that is we see here? Now this becomes important. We say the heart of all this is this, but inner heart of all this is this f function. F function works this way, that you have input that comes from top, this R, 32 bits from R. So you get R32 bit. You expand this using some expansion function to 48 bits. Okay, now you have key of 48 bits, and now take this 48 bits and split this into 6 bits each 8 times, right? And then use something called substitution function and substitute this 6 bit by 4 bits. This substitution is nothing but simple mapping function, which is complex mapping function. 6 bits are mapped into 4 bits. How do you do that? And they have defined the method for that. Okay, so 6 are mapped into 4. Okay, a simple way is that use some kind of table for that. Okay, just a minute. Wow. Okay. Well, I think I missed one slide, I guess. We'll cover that in the next class because we have just 2 minutes left out. So, okay, all right. So we'll look at how substitution function works, because we'll use this also in AES. Okay, so idea is that take these 6 bits, okay, and then you create 4 rows and 16 columns. Take 4 bits out of these 6 bits, say x0 to x5. Okay, now this first and the last bit will define which row. Okay, and then remaining 4 bits in between will define which column. And you just take that, and here there will be 4 bits here, statically defined. So take these 4 bits and substitute these 6 bits by 4 bits. So you create a very simple table, which is called X box. Okay, so now of course there are other things, like we have expanded 32-bit to 48-bit. All these are given, and what we get is after n permutation we get the output. Okay, all right. So we will come back. So when we do this 16 times, and after inverse of initial permutation, we get 64-bit of ciphertext. Now, I know I've covered it very fast. We'll start from here. and then we'll look at some of the aspects. Okay, to summarize in next 2 minutes, DES was the dominant symmetric encryption algorithm from mid 70s to 90s, and it's very important because AES uses similar concept, however larger keys, larger size key, and design is slightly different. Key space is too small because 56-bit keys does not give very large key space. Okay, a simple solution hack of this is use this DES 3 times, then the algorithm becomes 3 DES. All right, so what we have studied so far is that encryption, we take input of n bit, it creates output of n bit, which is a block using k bit key. Decryption function is just inverse of that. It has to be correct, it has to be secure, and it should be fast. Okay. Okay, DES is now more or less obsolete, but many legacy applications are still using it. Okay, it is not IND CPA secure because it is deterministic. All right. Now in the block ciphers, we can take inputs of n bits or block size of n bits. Is this a limitation? Yes, this is a limitation. But we can split the message into number of blocks and then combine the output of these and get the ciphertext. Okay, now we'll look at in later classes how do we split it and what happens if the last block is less than n bits. We'll answer some of these questions. Okay, any question? Are you able to understand it? Is it going too fast?